There we go. All right. So yeah, no major announcements. We're just kind of winding down still, doing some fun special topics. So you should have watched the video on the coupled line coupler, and I kind of thought the book's treatment of that left a lot to be desired. So I tried to follow along with their derivation as best as I could. But there's kind of that big question mark at the end where they just kind of say certain things without proof. Because I tried actually doing some numerical simulation of it, and it didn't quite seem to work the way the book indicated there. So I think there may be a little bit of a whoopsie doodle on equation 783. Because I looked around on some other derivations, like there's some other professors' lecture notes you can find at like MIT and places. And what they seem to indicate is that that little expression is only true if you impose a quarter wavelength on your coupled line coupler there. So my goal is to have a homework assignment. Oops, excuse me. Got a bunch of gunk on my desk here. Get this out of the way. Just have a homework assignment posted by the end of the day, and we'll have it due like by the last day of class. And it's going to just cover some of the stuff we're doing today with a few little extra easygoing kind of problems, I suppose. So I had an idea for today's kind of practice problem here. Let's pull up the quizzes. Where is that? Today's the 23rd. There we go. So I'll do a quick screen share here. There you go. So I got this fun idea to do numerical simulation of a coupled line coupler. And I thought it'd be a little pretty straightforward kind of thing to do. So I got like most of the simulation kind of working as just sort of a demo of how the design process for this would have to work. So I think I got like 95% of it the way there. The last little stretch would be to do some kind of little FDTD simulation of the thing to show how it works. And I had it working this morning, and then I tried to upgrade it a bit to make it more accurate, and I wound up accidentally killing it. So we'll have to kind of go back through that again and rederive some parameters to at least get my simulation working again to show you how that works. But I at least got most of the basic parameters there that we can play around with. Another interesting thought that hit me is looking at some of the research on this. A lot of the numerical simulation involves that I could find, and after digging around for like a half hour or so, if you look up like a coupled line coupler, you see a lot of like full three-dimensional FDTD simulation using like integrated photonics, right? So a fun little exercise. You just go to Google and you look up coupled line coupler FDTD. You see a lot of like time domain analysis, but they use really complicated methods here. You know, Crank-Nicholson finite difference method, and the telegrapher equation. So this is kind of on the right path there, which is strange that they would use Crank-Nicholson method because there's perfectly good FDTD equations for the telegrapher equations already. So that's a little strange. But then you also see a lot of this sort of thing, evanescent waveguide couplers. So that word waveguide coupler means something different in kind of the world of waveguides than it does in transmission line theory. So you see a lot of this kind of full field approach where this is something where it's very similar to like fiber optic type stuff where you have two waveguides that are very, very close together and they're made out of dielectric, and the evanescent field from the one sort of bleeds over into the other. And it does very much the same thing that a coupled line coupler does. But when it's interesting when you see, here you go, here's a microstrip version. And from what I could tell, they're doing like full three-dimensional simulation of this thing. So I was kind of curious, is it possible to do a very simplified simulation just using nothing but the telegrapher equations and the appropriate characteristic parameters here? So that was kind of the idea I was going for today. And as I was digging around, I'm kind of curious, this might actually be something that's never quite been done before. So if anybody gets really motivated, you could probably write a paper on what we're about to do in today's class here. So this won't really be on your homework or on the exam, but it's kind of a nice exercise in terms of here is the theory. So what would it take to build a model that kind of actualizes this thing so that you can use it to actually design a real device? So let's kind of introduce the problem a little bit here. So let's go back, stop sharing, and we'll go to, oops, sorry, I didn't actually join. I got my camera plugged in. I forgot to activate it here. Hang on a sec. Let's go ahead and activate video now. There you are. I'm going to just pin that video real quick. So the basic idea for a coupled line coupler, you have some transmission lines made up, and you imagine something like microstrip, right? And you have maybe another microstrip over here. And if they're very far away, then for all practical purposes, they are isolated. None of the fields from the one will interact with the fields from the other. So this is going to be port number 1. We'll call this port number 4. Imagine, a signal being fed down this port here. And then they're going to come together, kind of like this. Let's see if I can do that. There we go. When you bring them close together, like this, there we go. Kind of darken that in. So you get this phenomenon of coupling now, where the voltage and the current here on this one line here starts suddenly bleeding over into the other because you have this mutual capacitance and inductance between them. So any sort of voltage and current over here is actually going to transfer energy into the other line. And then we kind of come back out again like this. Okay, and then we'll do something like that again. So they come together briefly, they interact with each other, and then they leave like that. So here is line number 2 or port number 2 and port number 3. So my initial intuition before I did the theory on this would be that you would maybe have this sort of dragging effect that would throw current and power down out this line over here. But the reality is kind of weird. It actually wants to go that way, which is kind of counterintuitive to me. And this is actually, if you set it up right, you should get no transmission out this other line. You make this like a quarter wavelength. So that's why this guy over here is the isolated line. This is called the through line over here. Then this is the coupled line, right? And then of course that's the input. So it's kind of weird how it wants to reflect backwards when you do that. But when I ran the little FDTD simulation, that's kind of exactly what happened when we did that. So the basic question is, how would I design something like this in real life? Okay, so let's suppose hypothetically we want a characteristic impedance of 50 ohms here, and of course 50 at all the other lines. So that's, we'll say Z0 is 50 ohms. What do I have to do to create a coupler here? And what will the coupling factors be? And that's not a trivial problem. There's a lot of interesting numerical simulation and work that has to go into something like that. So let's just start with just the basics. Okay, we're going to assume I have a microstrip, right? So sort of like our copper clad board. So we know our dielectric constant is going to be like 4.6, and that our velocity of propagation will be something like 0.55 c. So how do I design a microstrip line that will give me these parameters? So we've done this before. We know in advance I should get something around like 3-ish millimeters, right? But the real difficult part is going to be what happens when I bring this stuff together. So I kind of want to introduce some numerical simulations. So if you've taken numerical methods from me or Dr. Simpson, Some of this stuff should be a little familiar. And if you haven't, that's okay. You can still kind of follow along to see how the basic method works. Let's try recording. Sorry, that was embarrassing. Surprised that's the first time I've actually done that. There we go. So just for the sake of the record, if you're watching this later on the recording, accidentally hit the end button and killed the entire meeting rather than just stop my screen share. So let's go back to screen sharing. So where did I leave off there? You remember?
You ended it right when you were switching to your screen.
Oh, so I meant to screen share and I hit end by mistake. Is that what happened?
Yeah, so we've seen none of your MATLAB code.
Ah, okay. So what I have is a numerical simulation for a microstrip line. And if you've taken numerical methods, that's 5340/6340, you'll learn how to do electrostatic and magnetostatic simulation. So for those of you who've taken that class, this step should be kind of familiar. At least if you took it from me. If you took it from Jay Messina, I'm not sure how much she spends on the electrostatic stuff. She usually likes to focus way more on the FDTD side of things. But it's that same idea where you can use finite difference methods to calculate an electrostatic model. So that's what this little code here is doing. It just says simulate microstrip. And when you go through, it creates this class instance of an electrostatic simulation and then a magnetostatic, and it just fills in all the appropriate boundary conditions for a microstrip line. So I'm going to go ahead and just run that real quick, and you'll see the simulation looks like that. So if we zoom in here, you can see that is a little positive strip of copper. It's all at a constant potential, so there's no electric field inside of it. But you can see all the electric field coming out of it. And you can even see the little discontinuity here where there's the dielectric boundary. And you notice I've added all this kind of void space to make sure that there's like nothing around it to interfere with the calculation. And so that's the electrostatic simulation. And then over here, you can see I'm just doing the magnetostatic. So it's the same idea. It's actually the same equations and everything. You just have to interpret them a little bit differently. But there is some current excited on this strip here, creating a magnetic field. So let's kind of zoom in. So you imagine your thumb poking out of the screen and you follow the right-hand rule there. And you can see the magnetic fields are twirling around counterclockwise. Okay, so I have an electric field and I have a magnetic field. That means I can calculate capacitance and inductance. So there's like a number of different ways to do that. Some are more accurate than others. But if you look up here, you notice we do a Gaussian contour to calculate the total current in the microstrip line, because it has a fixed potential, but I don't know what its current is, and current is essential to calculating inductance, right? So it's just Gauss's law, right? You do that closed contour around this microstrip line that tells you the total current here. So that's all this stuff here. So you define this little box around it, and you pick out the indices, and you just pull out the tangential component of the magnetic field. You do a numerical sort of integral around all of that, and that tells you the current. And then there's some stuff happening here that's not really being used, so we'll get rid of that. So that is how you calculate inductance. So you do the potential divided by the current. There's your inductance there. For capacitance, you just add up all of the energy in the system, and you know that energy is equal to 1/2 CV squared. So that's how you calculate the capacitance out of that. And then your characteristic impedance is just square root of L over C, like that. So we come back over here. So we run that, and you can calculate. So you find my Z naught is about 50-ish ohms, 49.6, and my characteristic inductance, about 316 nanohenry per meter, and capacitance is about 128 picofarad per meter. All right, so that is sort of my default parameter, which we kind of already knew, right? We used all those approximate equations to derive those same parameters. This sort of simulation is just a little bit more rigorous, but it doesn't have the benefit of that nice closed form expression. So the next step is we need to calculate the even and odd impedances. So we'll kind of do that next step here. Odd mode impedances, like that. So let's see, this stuff over here needs to come back down over here. So it's doing the first calculation. Whoops. Oh, I gotta uncomment that. So let's start by, I'm gonna leave this at the same value here, like that. We'll ignore that for a moment. And I need a separation over here. So there we go. So let's skip that guy, and then we'll just return right here. So we'll plot the results. So there we go. So there is an even mode for the electric field and the magnetic field. So if we zoom in on that again, you can see I have two strips and they have the same potential now. So you can see the electric field sort of butting into itself over there. But that's what it means by the even excitation. So I've excited both of them with the exact same potential. And so you get some corresponding capacitance and inductance out of that model as well. So then you look over here, here's my inductant or my magnetic field. So you can see that same kind of behavior going on. And I'm free to kind of slide these two strips back and forth. So if I want a lot of coupling between them, I want to bring them really close together. And if I don't want very much at all, I would have to move them far away. So I could do something like, say, separate them really far. Okay, so that's 2.5 widths of separation there. So now the next step is we got to do the odd mode. Sorry, I'm not quite done yet. So that even excitation has its own, using the exact same math, you have to calculate its characteristic impedance using, so I have CE for, there's my capacitance, LE and inductance, and then my Z naught E for my even mode impedance. You notice I get 25-ish ohms by doing that. So that should make a little bit of sense, because by adding the second strip there and exciting it to the same potential, it's basically doubling my capacitance. You can kind of think of it in those terms, right? That is to say, if I took one strip and made it really, really fat, or just had two strips and kind of brought them close together, those are very similar systems, and we should expect the impedance to go down. Because that's what we saw on our models before, right? A thicker width meant lower impedance. So what's happening is the characteristic capacitance is going up, but from what I can tell, the inductance is probably, is it staying the same or is it going down? So we have LE is times 1E9. So now we have about 163 nanofarad per meter. What was it before? Here, let's run this calculation again. So we'll run both of them back to back just for comparison here. So there's by itself. So it's just kind of doing its thing. So then there's the even, there's the magnetic field. All right. So we had L times 1E9, and then LE times 1E9. So you notice the inductance is going down when you make the strips fatter. Does that make sense? And I'm trying to think, like, how does that intuitively make sense? Because you got to do a lot of dummy checking on this stuff to make sure we can follow along. So let's go ahead and look at, where is my video here? So I'm going to go back to my little video over here, pin video. So just kind of an intuitive dummy check. Here is a strip over here. So there's some voltage, you'd say plus V naught and then minus V naught at the bottom. Remember that capacitance is, what is it? It's Q over V, like that. So if I were to then fatten this thing, like by doubling its width, you would expect the capacitance to go up. So then the question is, what happens with the inductance? So inductance is flux divided by current. So does that make sense for inductance to go down? Because you know also for like a parallel plate capacitor, it's proportional to the width of these guys, right? So you imagine a tiny, tiny little guy. Does that make sense? Because it's my intuition is telling me that if I have the same amount of current here, but if I spin it out more, that means my magnetic field is going to get less when I do my flux from here to here, right? So you remember that I have to integrate the magnetic field across this little area here. So if I take that same current and I spread it out, my hunch, my intuition says the magnetic field intensity is going to go down, even though the current might stay the same. So what that would imply is my flux goes down, and so my inductance goes down. And then you have Z naught is the square root of L over C. So what you have is basically by widening this thing, your inductance goes down and your capacitance goes up, which means your characteristic impedance ought to go down. And so by kind of a loose analogy, you can say here are two strips back to back, but they have the same excitation here. That's very, very similar in nature to what would happen if I kind of connected them together. So that to me now intuitively makes sense. When you do the even mode here, you can see that my impedance went down because my inductance went down and capacitance goes up. Okay. And McAfee wants to scan for viruses, not now. So go back to screen sharing. So everything now is sort of jiving with our intuition, right? So we find that the even mode gives us a lower impedance. So now the question is, what about the odd mode? So let's just comment that out for now and comment that. And we'll do the odd mode here. You notice I just created another function that just says simulate microstrip odd. So it's going to do the exact same thing, but that other strip is going to be a negative potential instead of a positive. So what's happening is my field intensity is kind of dropping a bit because instead of having positive here and then negative on the ground, what's happening is this is a positive and the negative is over here and the ground is now a 0 volt reference here. So you got to be a little mindful of those little distinctions. So here, let's just try and fix that up anyway. I'm going to do a quick little tweak on my color map. So I'm just going to divide these guys by 2 because these are specifying the color limits. So then we'll just run that again. So that'll just bring out some of the color a little bit more. There we go. Boop, 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 boop. There we go. Okay, so you can see now I have positive, which means all the electric fields are bursting out of the left little microstrip over here. And then the negative, they're all kind of getting sucked into here. You can see also the ground plane has 0 volts here. So it's positive, negative, and 0 in this case. And you can see kind of there's this localized negative charge here with some localized positive, but they should balance out so that there's no net charge on this ground plane here. And then same thing over here with the magnetic field. You can see positive current coming out, so it's going counterclockwise here. And then the negative current going in is now wanting to go clockwise in the other way. So you then do that same sort of analysis where I can calculate, say, the total magnetic field energy here, or the total electric field energy, or you can do a number of different approaches. I need to calculate the equivalent capacitance and inductance here. So I need to calculate the total charge on that strip there and calculate all the flux coming through by doing the flux out of it. Or you can calculate the total electric field energy in this entire system. Both of those methods will work, just there'll be a few % difference between them depending on the precision of your model here. So what do we find? So now the question is, what should we expect to find actually? So should the capacitance in this case go up or down? And that's kind of an interesting question. So the intuition is that for the even modes, it went up. So should the odd modes also go up or should they go down? And the answer is when you do the odd, the impedance goes up a little. So originally it was 50 ohms, now we're suddenly at 65. So I was kind of struggling, like, does that intuitively make sense in that situation? And you can probably do a similar kind of hand-wavy argument about the capacitance now. It's not between this plate here and ground, it's between this plate and that plate there with this sort of floating piece of metal next to it. So if you imagine two parallel plates and they're kind of one above the other, you have a lot of capacitance. If you make them side by side, that will reduce your capacitance significantly. And then by similar arguments, your inductance will go up. And so your impedance now is all going up at the end of the day. So you can see my C odd, 1E12, is 64 picofarads, right? Whereas before it was, oh, right, I didn't run the simulation yet. L odd now times 1E9, 273 nanohenry per meter, or yeah. Okay, so now what we gotta do, we're gonna run everything kind of together here. And in order to make a matched system, I need this thing to equal my characteristic impedance, my original Z naught. So we're gonna do something like this. Remember, so we say this ensures a match at port 1, right? So this was the condition that allowed port 1 to be matched. In fact, and by symmetry, all of the ports will be matched if this condition is met. So you run the simulation. So first it's going to run the strip by itself, and it'll calculate all the parameters. And then it's going to run the even mode. So you see it's just crunching along real quick. I can turn off the plotting if I wanted, but it's there for a nice validation. Then it does the odd mode here, so you can see that. There's the electric field, there's the magnetic field, and then the end. Okay, so you'll notice I have a Z naught, which is about 50-ish ohms. I have a Z naught, or Z naught even, which is 25 ohms, Z naught odd, which is 65. And then we calculate this parameter here. So I just called it ZX. And we're at 40 ohms. Also, I think I may need to yell at my cat. Sorry. Yeah. Sorry, there's a cat scratching at my door making noises. So this is now a problem. How you notice I took the square root of the product there and I did not get 50 ohms back. So the book didn't quite go into detail on that. So but the question is, how do I now enforce that condition where they match again? So the question might be, well, what happens if I toy around with the separation? Like if I bring them closer together, well, that maybe have an impact. So we'll go ahead and run that simulation now. So you'll watch, you notice I brought them really close together. There you go. So, oh, now it's doing the odd. So you can see all these huge fields there between them. And you notice it didn't actually change the product very much. So moving them farther apart and closer together did not actually tweak the product of their impedances, right? Z naught E changed is still about the same. Z naught odd, they kind of change a little bit, but not really. And in fact, most of that change is probably some numerical artifacts of being closer to these walls over here or not. So, but you notice the separation didn't really change the product between them very much. So in order to change that, like they're coupling a lot more or less, but that product between their impedances hasn't been met. So what we got to do now is tweak some of the parameters a little bit. So one thing we know is my product of my impedances is too low. So one thing I can do to increase the impedance is squish down the widths a little bit. So we know if they squish the widths, then the impedance will go up. So presumably the square root of their product should also go up. So for example, suppose we run this again at 2.5 millimeters rather than 3. So what that means is I'm going to have the default lines at 50 ohms, but when I do the coupled version, even and odd, I'm going to change their width a little bit to squish them in. So we'll run that simulation. So there's the default. And then, so there's the even mode, and they're a tiny bit thinner now. I changed it by like 20%, 10% there. So now you look at ZX, and you notice it came up a smidge. Not quite enough, so let's do 2.25 now, right? So there's a little bit of trial and error here to get that product to match. There we go. So ZX, ooh, 47. So we're getting a little closer. Let's bring it in just a smidge more, right? And we'll just skip that first simulation now because we know that's not going to change. So we'll do the even and the odds again. There it goes. So ZX, ooh, 48. Oh, it's getting so close, right? So maybe 2.15 there. So simulate. Oh, so close. 48, 48. All right, let's just bring it down to an even 2 here. See what that does. Okay. And there we go, 51 ohms. It's kind of close enough, right? At that point. So that is one of like the first sort of design decisions you got to make. So what that now implies, we'll come back here. So up here, and these lines up here, we had W equals 3 millimeters, right? And that gave us an impedance of, oops, 50 ohms. But in here, so let's use maybe green, you gotta change the thicknesses there because we want the even and odd products to match. So what we found in here, so that was a W1 is what I was calling it here. So I'm gonna call this W2. So what we found was W2 is equal to about 2 millimeters. And so that gave me some Z naught even, and there was a Z naught odd. And the square root of their product now, so you say Z naught even times Z naught odd, was about close enough to Z naught. So you could fine tune it a little bit more if you really wanted to, but that is the goal. So that now guarantees a match looking into all of these ports. So how much time do we have? We got another 10 minutes. Okay. So that just, yeah.
Just out of curiosity, now that you've changed the width of the coupled strips, is it more or less sensitive to the distance that they're spaced, or is that still 6?
Oh, yeah, that's a good question. So what happens if I bring them closer together or make them further apart, right? So let's, so right now they're pretty close. Let's make it like a little extra. Let's make them farther apart, right? So we'll run that again. So from what I can tell, it seems to be relatively insensitive to that spacing. So ZX, so you see it didn't really change it very much. I just almost doubled their separation there. Whereas before it was 1.28, 5.1. So it barely changed by like a half an ohm to separate them like that. So it's pretty insensitive to that distance as far as I can tell. So that kind of blew my mind. So they will couple more or less, and you're even and odd, but yeah, that product between them won't really change a whole lot. So yeah, that's kind of a weird phenomenon, which I think kind of makes sense, right? Because kind of like, I don't know, intuitively, whether or not they're kind of close together or further apart, it doesn't really perturb the total capacitance or inductance between this system here. Like it'll kind of affect the fields really close. I think if you get them really, really close together, you'll see kind of a difference. So let's like smush them right up against each other. In fact, I can do even better than that. So you notice, yeah, that barely changed it by like an ohm to do that. So let's shrink it in even more. So now they're just like really cramped. And I might even blow up the simulation now because it needs to do a Gaussian contour in between that little bit there. So if you do it too close, there won't be enough grid samples to do the calculation properly. We'll see there. So that might have made an effect. Let's do one more double sanity check here. Just to make sure there's some grid samples in there. My hunch is that if they get really, really close together, then they'll start having an effect because all the fields in here are going to start fighting each other. But if they're reasonably far-ish apart, then the interaction there in the middle is relatively minor compared to all the other fields everywhere else. So you won't see a huge impact if you move them further apart after that. So you see, so now we're at 50 ohms again, right? And so if I just triple the distance, the amount of energy in the fields is kind of about the same at that point. So that's something interesting to think about. So ZX there. So now, yeah, it barely changed after that. So yeah, if you squish them really, really, really tight together, they'll have an effect. But once they're kind of separated, it doesn't really do much after that. So we've got like 5-ish more minutes because what I really wanted to do after this was do an actual FDTD simulation using multi-conductor transmission lines. But maybe this is for the best because at this point we're kind of done with all the main material and it's just going to be like, quote unquote special topics. Here, let me in the so I was thinking what might be interesting is Dr. First asked that we do at least one lecture on grounding, just grounding practices. But after that, it's just kind of up in the air of what we want to discuss. So one thing I thought would be really interesting is the theory of multi-conductor transmission lines. And it's basically exactly the same thing we've done, just with extra conductors thrown into the system. So again, you won't necessarily be tested on it or have to do homework on it, but it is something that's worth being aware of, that it exists out there, because this has been pretty useful for a lot of research, especially right now. I'm writing a paper with Dr. First's group that uses some of this theory to do some interesting modeling on transmission line effects for TDR. So let's do just a quick little overview. And then maybe if I'm very clever, we can do the simulation on Wednesday. But the basic idea is here is the ordinary transmission line model, where you have your signal line, there'll be some inductance, and I'm going to ignore the resistance here. And you had capacitance. And that was your lumped element model. And I guess, remember, you could hypothetically have your conductance here and a resistance there. And this one was R prime, G prime, L prime. So you had L prime, C prime, R prime, G prime, right? So this was basically your ground reference here, and then this was your signal line from here to here. So you had some voltage and current going through all the elements here. And then you did that limiting thing as you let your delta Z squish down to 0, and you got some continuous differential equations. A multi-conductor transmission line basically does the exact same thing. So here's my inductor, here's my capacitor. We'll just kind of go out. So again, I'm just going to pretend this is my reference line here. So those are plus, minus, plus, minus. There's a current here and a current here and so on. What if there's just another transmission line here doing its own thing? Kind of like this. Okay, so there's a voltage here. So we would call that L11, L22, C11, C22. Only when I have multiple conductors around, I might also have some crosstalk between them that looks like this. So we call that C12. Okay, and there's also some mutual inductance between these guys here. So I would do kind of the transformer notation where you would imagine this. And I would call that L12. So you notice, and I can do this arbitrarily. I could add like, 20 different lines, and each one will have one of these crosstalk terms to the others. But the three conductor line, so we call this a three conductor transmission line. And you just do the exact same derivation we did before. Remember, you just have, there's some voltage here with some currents flowing around, but you just have this extra voltage crosstalk between these guys here, and there's a little bit of extra current here, and you just have to account for those extra terms doing the exact same derivation by applying Kirchhoff's laws. And so you get sort of this generalized form of the telegrapher equations or telegrapher equations that have this sort of matrix vector notation to it rather than simple coupled PDEs. Okay, so that is the essence of multi-conductor transmission line. And I'm thinking that'll be kind of a nice discussion as a special topic where we just kind of go through the derivation to get the sort of generic telegrapher equations from a model like this. Because then what you can do is an FDTD simulation of it, just like we did before where we took that differential equation and we discretized it and did all that fun stuff. You can do it on this thing too. It's not that much of a conceptual leap to just add more things to keep track of there. So that's what I was trying to do when I put together this transmission line model. So I actually have like an FDTD code that does this exact thing. So what I'm going to do is just comment this stuff out here and give you kind of a brief example of what it looks like. So you notice you have a signal line here and a reference. So I'm just exciting the one here. And right now they're isolated, so there's no crosstalk between them. It turns out it's really hard to get a good model of crosstalk without kind of blowing up your simulation. So what you need to do then is fill in those matrix elements to get the crosstalk between them. And then the idea is you just fill in the appropriate parameters there for your coupled line, and we should hypothetically be able to simulate a coupled line coupler using this kind of FDTD model. So the only tricky part is using these electrostatic and magnetostatic simulations to insert the correct I guess, diagonal elements, though that L12 and the C12 there. And then what you'll actually see is the signal will come in here and you'll have a boundary where the coupler begins. You'll see kind of a reflection coming out of the other line with some transmitted energy. And then ideally you should get nothing kind of falling out the other side there. So you see we have line 1 voltage, line 2, and then line 1 current and line 2 current there. So right now that was just one line being excited with the other one isolated, so obviously nothing happened there, and that's kind of boring. So what you have to do then is you have to fill in those parameters. I have the L11, L12, so you notice I've just put in 0 for the coupling terms here. So that's why you got an uncoupled version. And then you need to put in these coupled line terms, but if you're not careful, you start violating the laws of physics. So this was my pitiful attempt to try and get something working. But if you watch, it's gonna explode probably. So it's gonna come in, and there's an actual boundary here where I'm trying to put the coupler, and it's unstable because I tried to give it parameters that aren't consistent with the laws of physics. So like I said, I had it kind of working, and then I played with it and messed it up by trying to use these coupled line parameters here. So my hope is by Wednesday, we can kind of walk through the derivation of how you get those parameters, and then we'll run this FDTD simulation and you'll see a coupled line coupler in action. And then what would be extra interesting is I don't know if anyone's actually done a model this way before, using multi-conductor transmission line with these electrostatic models to try and design a coupler. From what I could tell, most models seem to use some kind of full field simulation. Right, so like, whoops. So you can see like here is an FDTD analysis. I'm willing to bet if you dig into this, they probably did kind of a full field version of this and full three-dimensional FDTD kind of simulation of that. And this guy, you know, he's using Crank-Nicholson method, which is kind of weird and ancient. So at least it's odd to do that for multi-conductor stuff. I don't know, or for telegrapher equations. That'd be interesting to look into. But I kind of suspect if we got this model to work, you could probably make a research paper out of that if anyone really wants to look into that. I'd say there's about an 80% chance that would be kind of an original piece of work. So fun fact, if anybody's really interested in that, that'd be really cool. Okay, so that's all I have for today. I'll try and get our last homework project up by the end of the day today, and it'll be relatively straightforward stuff. So the special topics you won't really be quizzed on or tested on. It'll just be the power dividers and the coupler type stuff, and very basic stuff. You know, here are some design goals. How would you create, you know, a divider or coupler using microstrip, that kind of thing, like we did in class. Okay. So any big questions before we go? Other than that, you're free to go, and thanks for coming out.